Welcome to Mark's scheme. Some differential equations are hard, or even impossible, to solve exactly. So how do you trace the solution curve anyway? Euler's method. And it's beautifully visual once you see it move. Here's the setup. A differential equation, dy by dx equals x plus y. And the starting point, y of 0 is 1. The equation hands you the slope at any point you like, but it never tells you the curve directly. We want to trace that curve. Let's see the slopes first. At every point, the equation gives a slope, so we draw a tiny dash there. Blue where it's gentle, gold where it's steep. Fill the whole plane and a hidden structure appears. Drop particles into that field and let them flow, each one always following the local slope. They sweep out a whole family of solution curves, one for every starting height. Our initial condition, y of 0 is 1, simply selects a single one of them. Zoom in on a single step. The equation says the slope right here is exactly 1. We don't know the curve, so we make a bold guess. Pretend the slope never changes, and the path is a straight line, running off forever. Reality bends away. The true curve pulls upward off our straight guess almost immediately, so we don't trust the line for long. We follow it for just one short step, h, then stop and reread the slope. We step 0.5 across and rise by h times the slope, landing at 1.5, just below the true curve. That little gap is the error we accept for not solving anything. Now repeat that one step over and over. From wherever you are, read the slope. Step across by h, rise by h times the slope, and land somewhere new. Then do it again from there. Watch the staircase of tangent steps build. That gold staircase is Euler's approximation. Lay the true curve over it. The shape is right. It tracks the solution. But watch the gap. Each step adds a little more error than the last, so the shortfall grows as we climb. How do we shrink that error? Smaller steps. Start with h equal to 0.5. The course, jagged staircase, and a gap of over 2 at x equals 1.5. Now watch as I shrink the step continuously. The staircase tightens. The gap number tumbles toward 0, and Euler melts onto the exact solution. In the limit, as h goes to 0, they become one curve. The price is more steps. Accuracy versus effort. Here's exactly why the staircase falls short. Euler locks in the slope at the start of each step and walks in a straight line. But the real curve keeps bending upward as it goes, pulling away above the tangent, so the step lands below the true value. And that shortfall is the error. Whenever the solution curves away from its own tangent, Euler trails behind. And the smaller the step, the less room it has to drift. Written down, the whole method is one line. The next y equals the current y, plus the step size h, times the slope right where you're standing. In symbols, f of xn, yn is just the right-hand side of your differential equation, and x just marches forward by h each time. That pair of updates is everything. apply them again and again, and you generate the staircase automatically. Let's run it on a real exam question. The classic version. Given dy by dx equals x plus y, with y of 0 equals 1, use Euler's method with a step of 0.5 to estimate y at 1.5. Exam technique. Build a table, one row per step. Row 0, at x equals 0. Y is 1, so the slope is 1. Add 0.5 times 1, and y becomes 1.5 at x equals 0.5. Row 1, carry 1.5 down. Now the slope is 0.5 plus 1.5, which is 2. Add 0.5 times 2, giving 2.5. Row 2, slope is 1 plus 2.5, 3.5. Add 0.5 times 3.5. That's 1.75, and g reaches 4.25 at x equals 1.5. That's our answer. Y at 1.5 is approximately 4.25. One last idea. The doorway to our next video. When two quantities feed each other, a coupled system, the slopes form a rotating field. Euler still works. Just step x and y forward, together each tick. The true path here is a perfect circle. Watch Euler try to trace it. Each straight step throws the point a little outward, and the error compounds into a spiral creeping away from the circle. That drift, and how eigenvalues predict whether a system spirals in, out, or loops forever, is exactly what phase portraits reveal. That's next time. So that's Euler's method in full. 1. The equation gives you the slope at every point. 2. Step along that tangent, y plus h, times the slope, again and again. 3. Smaller steps mean a closer fit or egg work. 4. Reach for it whenever there's no neat exact solution. It's a brilliant internal assessment, or paper 3 tool. Model something real and step it forward. Next time, we'll see what those coupled systems do in the long run with phase portraits and eigenvalues. For more, that's markscheme.app. See you there.